All right. Well, hello again, everybody. Today we're going to continue talking about interest, in particular compound interest. I had a couple of notes before just remarks on the semester, general notes before I start. First, your final project is on Blackboard. You can find it under the course materials, and it's even got a little tab. Actually, I'm not sure it's under course materials, but it's got a little tab that says final project. So you can go and check that out. You know enough and to get started on some things, but you don't know everything. Today we're going to finish our section on interest, and the remaining sections which you'll need for the project are your retirement savings, and debt. What kind of debt you'd go in if you were going to mortgage a house, things like this. So yes, if you haven't taken a read over that final project assignment, it's a personal. So you either say what you would like to be doing in 10 years down the road, or what you might be doing, or create a completely fictional situation, and then calculate a bunch of the things that we've been talking about based on that, pretty much. So I'll let you go and read that over. And the quizzes have been looking pretty good. I'll grade the second round of quizzes tonight, but yeah, so well done on those. Remember to be signing it. You can sign in. I'm on Teams every Tuesday and Thursday from 11:50 until 11:40 until 12:55. One person has signed on so far for our 3 weeks of lectures that I've been on there. So really, if you're having trouble with any of these things, questions, sign on. Reach out to me. Good. All right. Well, let's begin. Good. I'd like to turn on Do Not Disturb so that nobody bothers me. So yes, these are the couple of notes that I was just talking about. Final projects are now posted, and you can get started. Sign into Teams if you've been struggling with any of the information. The apportionment stuff, I'm still happy to go back and talk about apportionment, because that was interesting and fun information. But today, our topic is section 10.3 on compound interest. So this is really probably the more important form of interest. If you remember last time, we talked about simple interest, which pops up sometimes, but definitely not as often as compound interest pops up. But it was a good way to ease into this topic. So let's recall what that was. So recall. So you have an initial investment. All of these interest problems, you have an initial, either an investment that you make and will be making money off of, or you have a loan that you take out and will have to be paying more money back, right? And we call that initial investment or loan the principal. So we have a P, which is your principal. This is the initial investment loan. And then we had the APR, which I always forget exactly what it stands for. It's the annual percentage rate. And so this is the interest. This is how much of your of the percentage. This is the percentage of what you have in the account, which is added in interest every year, because it's annual. So annual means year, and the percentage rate, this is like your interest rate in a percentage. And so remember, we had R, which was well, in the simple interest case, R was your annual percentage rate expressed as a decimal. So R, which is usually the APR as a decimal. In general, R is the interest rate. So we'll be using that again today. And T, remember, is the term of the loan. The term of the loan / investment. And T we were measuring in years. Measured in years. And so with just this information, we did all of the stuff about simple interest. So last time, we had simple interest. And the idea of simple interest was that it accumulates based only on the principal. The initial investment. Based only on P. Right. So that means that when simple interest, we had the interest that you accumulate over T years is going to be the principal multiplied by the interest rate as a decimal times the number of years, T. Good. So you will pay back, if you took out a loan, or be paid if it was an investment, the original principal plus the interest which is accumulated. And now that we have this formula for the interest, basically what you're receiving back is the principal multiplied by 1 plus the interest rate times the number of years. Good. So this was our formula that we got for simple interest, and you can go back to the last lecture if you don't remember how that worked. Okay. Now compound interest. So the difference here is that compound interest not only does the principal generate interest, but so does the previously accumulated interest. So it's like after 1 year you accumulate the normal amount of interest, the principal times the interest rate. But then the second year, you're going to accumulate interest based on not just the principal, but the principal plus the interest rate for the first year. So every year the interest is getting more and more and more and more because you're taking a percentage of a bigger and bigger number. That's the idea. Not only does the principal generate interest, so does the previously accumulated interest. All right. So this means that we'll have to choose how often that interest is compounded, right? Because if the interest grows every time we add interest to the principal, then if we do that more often, then our interest should grow more often, and so we should be paying or receiving more interest in total if it's compounded more often, right? This means we must choose how often interest is compounded. And this could be anything from yearly, which is pretty average, to quarterly, 4 times a year, even down to daily or continuously, which is what we'll lead up to with this lecture. How often the interest is compounded. Yearly, daily, continuously. I put continuously with question marks after it because that's so if it's compounded yearly, we can have a pretty simple formula to figure out how much the interest will be at each step and how much interest you will have accumulated over the course of T years. But if it's being accumulated, but if the interest is being compounded continuously, well then how do you calculate that? So that's what we'll get to. So, in general, compound interest accumulates much faster than simple interest. So this means that if you're the investor, then you want compound interest, because that means if you'll be making more money off of the money you invested. But if you're taking out a loan, then probably you would rather simple interest, because that would mean that you would be paying less in interest back on your loan. Good. So let's do an example. I think all of this will be much more easily processed in terms of an example. So, example. Let's say, oh right. So I wanted to just make a note first that simple interest. We had examples. We had bonds and loan sharks. These are the two very common occurrences of simple interest. Compound interest really applies to most everything else. For compound interest, we have examples like CDs, which we'll talk about, certificates of deposit, all of your college loans, all of your what other examples of things? Trust funds, retirement accounts, etc. Okay, so in our first example, we'll talk about a trust fund. Good. So, say you have a trust fund, which has been collecting interest at a 6% APR, compounded annually. Okay. So maybe a family member started this for you, and let's say they started it with a principal of $5,000. Started by a family member at your birth with $5,000. Okay, so that's going to be your principal P. So maybe it was so as lots of trust funds are, maybe you couldn't touch it until your 18th birthday. So say you have a trust fund. Yep, 6% APR, 5,000 principal, and you aren't allowed to touch the money until your 18th birthday. How much will be in the account then? All right. Well, let's start to figure that out. Okay, so let's do it again. So just writing all that out in math terms, because the words are they get in the way sometimes. So remember, we have an APR of 6%, and we have a principal of $5,000, and the term is 18 years. Okay. Well, we can figure out how much interest is accumulated in the first year, just like we did with the simple interest, right? Because the initial amount is the principal, and we don't have there's nothing else to accumulate interest on other than the $5,000 which was put in there from the beginning. So, so let's say that at 0 years, when you're born, we have the principal, which is $5,000. Okay, so after 1 year, how much is going to be in the account? Well, you're going to have the principal plus the interest, which is accumulated on that. And the interest, I, is going to be 6% of 5,000, right? 6% of 5,000, which is 0.06 times 5,000, which is what? Let's go to our calculator. 0.06 times 5,000, which is 300. Okay. Sorry. Does that seem right? 0.06 times 5,000? Yeah, okay. Good. So that means that you will have gained 500 plus 300, and so that's 800. But really, I'm not going to be as interested about the numbers here yet, because I'm not interested in how much you have after 1 year. I'm interested in how much after 18 years. And I don't particularly want to continue down this process, right? So the second year, you're going to add interest based on this 800, but why don't we write it in a different form? Remember that after 1 year, we have final amount, F, which is P times 1 plus R. So this is going to be P times 1.06, right? Because here R is our APR expressed as a decimal. Okay. Good. So that's 5,000 times 1.06 after the first year. Good. And that is, you can check, that's going to be exactly, oh my goodness, 800. I was really screwing this up. This is 5,000 plus 300, which could give us 5,300. Big difference. Okay. Good, but let's just leave it at 5,000 times 1.06. So now the next year comes around. And after 2 years, let's call it F2. Let's call this one F1. What are you going to have? Well, you're going to have the amount of money that you had after 1 year plus the interest that you accumulate on that first year's money. So now the interest is going to be 6% of F1, which is 0.06 times, and remember F1 was 1.06 times 5,000, right? And so what we're going to have is that F2 is actually going to be our principal amount of 5,000 times the interest rate. So this is F1, 5,000 times 1.06 times 1.06, because that's how you add 6% of this number to it, right? Multiplying by 1.06 is like adding 6% of a number to itself. Remember that. So remember, multiplying by 1.06 is adding 6% to itself. 6% of a quantity to itself. All right. And so now we can see a pattern, actually. This is why I didn't really want to do out the 5,300, but instead just look at this pattern. So after 0 years, you have $5,000 in there. After 1 year, you have $5,000 times 1.06. After 2 years, you have 5,000 times 1.06 times 1.06, because you're collecting interest on this whole sum here. And so after 18 years, what do you think we're going to have? After 18 years, our F sub 18 is going to be 5,000 times 1.06 to the 18th power. Yeah, so this is 5,000 times 1.06 squared. And so here, we're raising it to the 18th power, because this is really like 5,000 times 1.06 times 1.06 times 1.06, 18 times. So that's really what's going on here. $18 times. Okay. And so, why don't we put this in our calculator and find out what our final amount is? So now, if we take so let's do 1.06 raised to the 18th power is 2.854 something. I'm going to multiply that by 5,000. And we will get 14,271 and 70 cents. Because we're going to round. So this was, what was it? 14,271. And 70 cents, I think, is what it rounded to. Yeah, 69.5 rounds up to 70. Good. So this is how much money you will have after 18 years in your trust fund. That's quite a good deal, right? You've made almost 3,000 or 3 times as much money as you had when it was started for you. But it doesn't. It gets better than that. Now you have the opportunity, once you're 18, to take out that $14,000 and be a little bit ahead. But what if you decided to just forget that you ever had that trust fund and leave it to accumulate money until you were, say, 60 years old? This is a pretty good idea. Maybe you didn't even know you had the trust fund to begin with, and so you'd like to know how much money would you have if you wanted to put that towards your retirement. What? If you wanted to wait 60 years to touch it. Well, now we have we just do the same thing that we were doing before, except instead of raising it to the 18th power, we'll raise 1.06 to the 60th power. So then we'll have f sub 60, the amount after 60 years, is going to be 5,000 multiplied by 1.06 to the 60th power. And when we do that here, 1.06 to the 60th power, and we'll multiply that by the $5,000 that was principal. And look at that, nearly $165,000 will have accumulated from just your 5,000 that you had in there at the beginning. So that's 164,938. And I don't know, 45 cents. All right, so that's quite a big number. I mean, that's a big difference. Yes. So don't touch it. You didn't have before. And I just want to show you what happens as we change some things around. So what if the initial investment had been $10,000 instead of $5,000? Well, then let's just do the same old calculation. We would have had after 18 years, you would have had 10,000 times 1.06 to the 18, which we can do out here. 1.06 to the 18 times 10,000. 28,543. And 39 cents. All right. And here's actually something that you can notice. This should be the same number. So before we did 5,000 and now we're doing 10,000. So this is twice 5,000. And so actually this number is going to be exactly twice what our original one was. So here we had, here I can zoom out and then you can see it. Here we had 14,000 up on top, and here we have 28,000 down on bottom. So it is exactly twice the quantity. F60 is going to be 10,000 times 1.06 to the 60th, and instead of putting that into our calculator, well, we can just go up here and double 164,000. So let's say it was 165,000. Now I'll just double this. So that should give us 90 cents when you double the cents. Double 8 and you get 16. Carry the 1. 7. 18. 9. 6 times 2 is 12. So we should get 329,090. Just a bit of mental math there. Good. That's a lot of money. So maybe you should have asked your uncle to invest $10,000. But you were 0 years old. How are you going to do this? I don't know. And so one more thing is, what if our APR had been twice as high? Not the initial investment, but what if our APR had been 12% instead of 6%? Well, let's do it out. Would you think it'll still double, or will it be different? Now, F18, do the same thing. So now our we're back to having $5,000 initially invested, but now our rate that we're multiplying it by is 1.12, right? Because if we multiply 5,000 by 0.12, we get 12% of it. And if we multiply it by 1.12, then we get 12% of it added on to the 5,000. Okay, I'm going to keep on repeating that because I know it takes a little bit to stick in one's head. Raised to the 18th. Let's see what that comes out to. Multiply that by 5,000. 38,449. And how many cents? 83. Okay, so how does that compare? That's actually to that one. Well, that's actually higher than we would have had after 18 years with $10,000 invested. So already you can see that the APR makes a much bigger difference than the initial investment. So pay a lot of attention to your percentages when you get a loan or an investment, not just the amount that you're investing, because those percentages are what really make the big changes. And we'll see that when we do F60 here. So if you had invested $5,000 in an investment in a trust fund which accumulated 12% interest compounded annually, then you would have 10,000 times 1.12 to the 60th power, which is $4 million. $4,487,984.67. That's more than $4 million. Of course, that's a very high APR. 12% is pretty high, but this is how you can calculate these things. So note, P and F vary proportionally. That's what I was just saying. Double P and we double F. APR and F are not proportional. As the APR changes, the final amount can vary quite a lot. Okay. Good. So this gives us our annual compounding formula, which is going to look a lot like our simple interest formula, but notice the difference. So our simple interest formula was P times 1 plus RT. And now our compound interest formula is going to be P times 1 plus R raised to the T. That's the big difference. So now our compound interest formula F is equal to P times 1 plus R to the T, where R is the APR in decimal form and T is the number of years. Okay, so this is a good one. Let me just do this. This will be fun. Fill color. Good. Now you'll all know what's going on. Okay. So what can we do with this annual compounding formula? compare to simple interest formula F equals P 1 plus R times T. Good. So what's a real life example? So here's a real life example. Certificates of deposit. Or a CD. A certificate of deposit is an investment. It's a lot like a hybrid between a savings account and a bond. So much like a hybrid between a savings account and a bond. So it's like a bond in the sense that you, like a bond, you lend money to a bank or credit union for a fixed amount of time. That's the interesting thing. A fixed amount of time at a fixed APR. So bonds are like that too. When you buy a bond, you know the APR, you know the amount of time, and it will accumulate simple interest, so you can even just pay it all back in one lump sum. A certificate of a deposit is like that. So you have a fixed amount of time that you buy it for. You have a fixed annual percentage rate, and it's just the thing is, instead of paying it all back in one lump sum or calculating the interest based on the initial investment, now the interest is going to change depending on the number of years you have it, etc. So good. Unlike a bond, interest is compounded okay. So it's also kind of like a savings account in the sense, like a savings account. These are safe. And by safe, I mean to say they're guaranteed by the government. And moreover, they're at a higher rate of return. Like a savings account, these are safe. Unlike a saving, but with higher APR, and you may not withdraw early without a fine, without a fee. Okay. Good. So let's do an example of that, and then we can calculate how much you might make on a CD. Good. So an example. So say you invest $1,500 in a CD with APR of 4.8% compounded annually. Okay. So let's look at how much you might make off of a 1, 2, or up to 15-year CD. 10, and 15 year CD. And we'll make a little table. So, good. Let's do that. So here we'll have the time, and here we'll have the amount of money, F, which we're going to use our formula from up here. F is P plus 1, P times 1 plus R to the T. So here, if our principal is 15,000 and R is 0.048, right? So R is the APR expressed as a decimal. Then F is going to be 15,000 times 1.048 raised to the T, right? 1.048 is precisely 1 plus R. When R is 0.048, then 1 plus R, 0.048, then 1 plus R is 1.048. Good. And so, let's do some calculations. For 1, 2, 5, 10, and 15 years. Well, firstly, let's try after 1 year. So 1 year is just going to be 1,500 times 1.048 raised to the first power. So that's just 1,500 times 1.048, which is going to give us 1,572. So $1,572 after 1 year. How about 2 years? Well, then we'll raise 1.048 to the 2. So 1.048 squared is 1.0983, blah, blah, blah. We'll multiply that by 1,500 to find, after 2 years, you would receive 1,647 back. 1,647.46. Okay, so after 2 years, how much have you made? Well, you can just subtract 1,500 from this to find that you made $147, right? Okay. So again, for 5, we'll do, well, I won't do all of these for you because I've calculated them already. So 1,500 times 1.048 raised to the 5th power is 1,896 and 26 cents. Okay, do 0 cents there. After 10 years, you will have made 2,397 and 20 cents. And after 15 years, let's see what we get. So 1.048 raised to the 15 gives us 2.02 blah blah blah. Multiply that by 1,500 and we get 3,030 and 47 cents. This is an interesting trick. So if you notice, after 15 years, you roughly double your money. You invested 1,500 and you get 3,000 back. So note, after 15 years, you double your money. In fact, we have a little formula. In fact, it doesn't matter how much you invest initially. Because of the proportions that I was talking about, these the fact that the P and F are proportional, with a 4.8% APR, you will always double your money after 15 years. We have this funny thing called the rule of 72. the rule of 72, which basically says if you want to know how much time it would take to double your money, how long it will take to double your money, you don't need to know P. It will take, you divide 72 over the APR, not expressed as a decimal, but as a percentage, is the number of years to double your money. And as it turns out, if we do it in our case, it's exactly that. In here, 72 divided by 4.8%, because that was what our APR was, remember up here. Here, 4.8% APR. Divide 72 by 4.8, and as it turns out, you get exactly 15. Fascinating. That's just a funny side note. So this is really the gist of compound interest. All of the rest of it comes from variations on this compounding annually thing. Because once you know how to compound it annually, you can compound it monthly, daily. We'll do a couple examples of that, but it's really not such a big change. It all comes down to this raising to the power of t rather than multiplying by t. Okay, so let's talk about general compounding now. Not just every year, but maybe every month or 4 times a year. So we may compound interest more often than annually. Interestingly, just because you're compounding more and more often doesn't always mean that you're going to be making a lot more money. So you might think always lead to more interest. You're right. But maybe not as much as you think. So what I mean by that is that the curve kind of levels off. The curve levels off. And so even though the difference between the money you make on simple interest and the money you make on compound interest is quite drastic, the difference between what you make when it's compounded annually and what you make when it's compounded daily even is actually pretty insignificant. So we'll do a couple of those examples and we'll see what happens. So let's go back to our $1,500 certificate of deposit. So back to our $1,500 CD example. So now, what if instead of being compounded annually, your interest was compounded quarterly? What if interest at 4.8% API was compounded quarterly? So the only thing that changes here is that your 4.8% was your annual percentage rate, interest rate, APR. But now, if your interest rate is 4.8% annually, what's it going to be quarterly? Well, then it's going to be 1/4 of 4.8%. Then your interest rate is actually 1.2% per quarter. 1/4 of 4.8%. So now we're gonna have r, little r, be 0.012 to represent that 1.2%. This is your interest rate per quarter. And so if we want to calculate it now, we can just pretend like we were back in the annual compound interest situation, except for that every year is now a quarter, and and our rate is now a quarter of what it was. But still, so after the first quarter, our CD has, so our initial investment was 15,000 times 1.012, right? So this is just the simple interest for the first quarter. We just do 12%. This is 12% of 1,500 added back on to 1,500. Okay, and maybe I won't do that out right now. So after the second quarter, F is going to be 1,500 times 1.012. That's your first one, multiplied by 1.012. Right? Because that's what happens when we compound interest. We now charge interest based not just on the principal, but on the whole sum that was in the account at the time the interest was charged. Good. So this is the same thing as 1,500 times 1.012 squared. And so, after the 1 year, which is 4 quarters, we have F4 is 1,500 times 1.012 to the 4th, which is precisely 1,500 times why don't I do this? 1.0. It's kind of important if you're just using one of these little calculators here that you do your order of operations right, because if you do 1,500 times 1.012 and then raise it to the 4th, you will get a very different answer than 1.012 to the 4th times 1,500. So that's a really careful thing to be careful of. 1,500 times 1.012 to the 4th is not the same as 1,500 times 1.012 to the 4th. Big difference. Okay. Order of operations. PEMDAS. Okay. 1.012 raised to the fourth times 1500 is 1,573 and 30 cents. 1,573 and 30 cents. And so, actually, we can make a chart, very much like our other chart, and calculate how much interest we'll have on a 1 year, 2 year, 5 year, 10 year, and 15 year CD. So on a 1 year, 2, 5, 10, 15 year CD, we'll do these calculations. T, 1, 2, 5, 10, 15, and 1 we've just done. We got 1,573 and 30 cents. Now, what's our formula here? This is going to be 1,500 times 1.012, which is our new rate, raised to the number of quarters that we go through. So I'm going to use capital T to be the number of quarters. So T is not T. T is the number of quarters. So maybe it would even be better. Maybe I'll do this. I'll make a column that's T. Oops, that's weird. T, and that's going to be 1, 2, 5, 10, 15, and then the number of quarters. So if there's 4 quarters in a year, we can just multiply these by 4. So that's 4, 8, 4 times 5 is 20, 4 times 10 is 40, 4 times 15 is 60. And now when we put these in, these are 1,500 times 1.012 to the 8. So now we do 1.012 raised to the 8th. Multiply that by 1,500. And we get 1,650 and 20 cents. So 1,650 and 20 cents. And the other ones I had written down still. So this was $1,904.15. After 10 years, you made $2,417.20. And after 15 years, you made $3,068.47. Interesting. This is actually not so different than our original table. You'd think that maybe if it was compounded 4 times a year instead of once a year, it should change. So the amount of money you have after 15 years should probably change quite a bit. But it's not so different. This is $3,030 and 47 cents. And now we got $3,068 and 47 cents. That's $38 more, but it's compounded 4 times as often. So that's kind of surprising. This should be kind of surprising. Not so different from annually compounded interest. And what if we were going to do 12 months, monthly, compounded monthly? So remember, before we divided our APR by 4. So now R is going to be our APR divided by 12 expressed as a decimal. So that's, remember, divided by 100. So this is going to be 4.8 divided by 12 divided by 100, which is going to be 0.4 times 1 over 100. So our rate R is going to be 0.004 now. And instead of multiplying every year by the 4 quarters which are in it, now we're going to multiply every year by the 12 months which are in it. Okay. So now F is going to be your principal times 1.004, and we had a principal amount. It was 1,500. Multiply that by 1.004 raised to t, where t is now the number of months. Okay. So let's we can go back then and just change our table. So why don't I do another table now? T, and F equal to 1,500 times 1.004 raised to the t. So now, after 1 year, we have 12 months in a year. 2 years, there are 24 months. 5 years, there are 60 months. 10 years, there are 120 months. And 15 years, 180 months. Okay. And so if we do out these calculations now, if we do 1.004 raised to the 12th, multiply that by 1,500. Right. We get 1,573 and 60 cents. Is that what I said? 73 and 60 cents. And yet again, this is quite amazing. Only 30 cents of difference there. 30 cents of difference. Nothing. After 2 years, 1.004 to the 24th times 1,500. So 1,650 and 82 cents. And I'll keep on going down. This one is 1905, 96. After 10 years, you've got 2,421 and 79 cents. And after 15 years, $3,077 and 23 cents. So now it's being compounded 12 times as often as it was when it was being compounded annually, and still the difference after 15 years is only between 3,077 and 3,030. It's not so much at all. However, remember, the difference between that and the simple interest version was huge, right? So that's the difference. So the difference between compounding monthly and compounding annually is small. But the difference between simple interest and compound interest is big. And so now I'll give you a general compounding formula just to formalize what we've just been doing. Alright, so that's going to be your final amount after however many terms, after capital T terms, is going to be your principal times 1 plus little p, where little p is going to be your APR divided by the number of times it's compounded per year as a decimal, raised to the t, where t is the number of times compounded and p is the APR divided by number of times compounded annually. And that's expressed as a decimal. Okay. So, yes, you can go back and look at this formula whenever you're feeling sad or lonely in this time, and you just need a little bit of financial math to get you through. Good. So, one last topic. I will really breeze over this one. This is continuous compounding. And as much as I'd love to talk about it, this is a subject for Math 19, not Math 17. This is really a calculus topic, and you need calculus to make sense of it. But I'll just give you the formula for it. So, continuous compounding, instead of discrete intervals, interest is compounded infinitely often. And in order to really compute this, we need calculus. In order to compute the formula, we need calculus. So I will simply state. Good. So that's it. So here's the formula. And this is going to say that your final amount is going to be the principal amount times e to the RT, where again t is number of years and r is APR as a decimal, and e is our irrational number e that we talked about with the logarithms. It's a 2.71828 blah blah blah. Mysterious. Good. That should be mysterious. But I'll just make a note that so what if our 1500 CD received continuously compounded interest. Then after 30 years, 15 years, we have F equal to 1500, our principal, times E to the R, which was 0.048, right? Our 4.8% APR, times T is now the number of years, which is 15. And what's interesting about this is we can use this formula even if we don't have like a whole number of years. We could have a CD for like 2.5 years and we could still calculate the interest compounded continuously like this. So here you can still use most calculators to do this. So what I would do is do the order of operations back. So first I would do this one, and then I'll click the E button, and that will raise E to this power. And then I'll multiply by 1500. So that's 0.048 times 15. And then I'll click E. Oh, no. Gotta be careful with these kinds of calculators. Times 15 equals 0.072. E to the 0.072 equals 2.71. Oh, no. This isn't what I want. So that's E, and I'll click raise to the power of 0.72. Better. So there's a number. And then I'll multiply that by 1500. And what do we get? $3,081.65. Oops. $3,081.65. And again, this really doesn't change so much from compounding annually. It's only $50 more after 15 years. Even when it's compounded constantly, infinitely often. Good. So a couple quick notes before I sign off here. And that's on annual percentage yield. So you might see, instead of APR, you might see APY instead of APR. They're really very similar numbers. This is the annual percentage. I'll just write down what it is, and I won't talk about it too much, but this is the annual percentage increase on the value of an investment or loan when both, sorry, so that's a little weird, when both the APR and frequency of compounding are taken into account. Basically, this helps us compare loans. So, like, if you had been told you could get a loan that had 4.8% APR and compounded daily, versus a loan with a 4.75% APR which compounded yearly or maybe continuously. So it just helps you compare, basically a way of comparing loans with different APRs and different frequencies. Okay. So there's an example in your book. It's really not that hard to follow. I just don't think that I want to confuse you about that kind of thing. We'll just use APRs. Are pretty good. We've already done the other stuff. And yeah. So Yeah, I guess, and there's a section in your book on savings accounts too, but they really don't say that. It's not. I think you can go and read about savings accounts if you want to. The idea is that you have a lower APR in a savings account, but you can put money in whenever you want, take money out whenever you want. So there's no term. Interest is usually compounded continuously. The only thing that's really against you in a savings account is the APR, the interest rate. So, so savings accounts accumulate continuous interest with no term and yeah. So no term, and you can withdraw / deposit whenever. The only thing, but they have very low APRs. So not much interest is accumulated even when compounded continuously. All right, so that's compound interest for you. I hope that was helpful. Good. I'll see you on Thursday.